Okay, welcome to day 2 of our probability lessons. Okay, what we're going to be talking about instead of simple events like yesterday is we're going to be talking about exclusive events. And so you're going to pay a little more attention to what's happening. What we're going to talk about first though is our warm-up, where we add and subtract fractions. So pause now to try your warm-up on your own. The key when we're adding and subtracting fractions is their denominator has to be the same. So there is a pretty quick way to do this. If you have two very different numbers like 8 and 5, I'm going to multiply this one by 8 over 8 and this one by 5 over 5. Okay, so what that will do, okay, is take my negative 15 times 5 on the end over there, and I'll get negative 75 over 40. And we'll take my negative 13 times 8 and get negative 104 over 40. Now that the denominators are the same, I can just do negative 75 minus 104, and I get the glorious number, negative 179 over 40, which is not reducible. It just chills. All right, I could do the same thing on number 2 with an 8 and a 2, but I could also say, hey, I'm going to make 8 into 2. I just have to multiply by 4 on this one. So that'll save me a little time, because I can leave this one alone. I'm subtracting a negative. Keep that in mind. It seems a little subtle there. So when I have negative 17 minus negative 20, I end up with 3 over 8. So that's the answer to that one. Also irreducible. 3 is a bit of a lifesaver because the denominators are the same, so I just have to make sure to do order of operations correctly. 1 minus 13 plus 1 is negative 11 over 8, also irreducible. Okay. Last problem. We have 8, 2, and 3, so I want to think for a second. I don't want to multiply everything by really big numbers. So let's think of a number that goes, that 8, 2, and 3 all go into, and that would be 24. So if I make my denominators 24, what that means is I need to multiply the 27 over 8. I'm going to multiply that by 3. Sorry. Over 3. So it would be 27 times 3. 27 times 3 is 81. All right, to get 1/2 to be having a denominator of 4, I'm going to multiply by 12. So I'll have minus 12 over 24. And our last one, I'm going to multiply this one by 8. Okay, so negative 4 times 8 should be negative 32. And 3 times 8 is 24. So I now have 81 minus 12 minus 32, which is 37 over 24 as my final answer. Okay, just a good review of adding and subtracting fractions there. All right, so one of the things that a lot of our probability problems are going to have are cards math. So talking about cards in a deck as your sample space. If you do not know a lot about cards, here is a summary about cards. There are 52 cards in a deck. There are 26 of each color. 26 of them are red and 26 are black. There are 4 suits, okay? Hearts, diamonds, clubs, and spades, okay? So that means there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades in each deck. Hearts and diamonds, this is essential. Hearts and diamonds are red. Clubs and spades are black. Okay? That is always true. All right, and all your cards are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen, and king. If you do not know about card math or have this memorized, I strongly suggest you write it down somewhere because there are card questions on the test. So I don't want you to miss out on those because you're not comfortable with knowing what's in a deck of cards, okay? Now for the important thing we're talking about today. All right, we're going to be talking about two kinds of events. There's mutually exclusive events, all right? So think about when someone is exclusive. That means they're alone, okay? Stand apart. So two events that cannot happen at the same time, okay? So an example of a mutually exclusive event would be turning left and right at the same time. You cannot do this. I cannot physically make myself split into two people. Another example of mutually exclusive would be tossing a coin and getting heads and tails. You will either get heads or you will get tails. You will not get both. A more common example of mutually exclusive events is if you draw a king from a deck of cards and an ace. You cannot draw them both at the same time because a king and an ace are always two different cards. Okay? However, our key today is we want to think about things that are not mutually exclusive. They are two events that can happen at the same time. So if you turn left while scratching your head, you can do both. Okay? You can do something like pick up two different coins at the same time, or draw a king and a hearts at the same time, because there is a king of hearts. There are other kings that can be described by another detail. Okay? So let's look through some examples of these. Okay? Drawing a king from a deck of cards is an exclusive event. Okay? And the way that we know is because there are 4 kings in the entire deck of 52 cards, which does reduce, okay, to 1 over 13. Okay? Now let's think about it. Can you draw a king and a queen at the same time? No, you cannot. Okay? So that is exclusive as well. Okay? But it's also impossible, so we can't calculate the probability because you can't draw a king and a queen at the same time. However, if we change the question to drawing a king or a queen, okay, it's still an exclusive event. Okay? But what you can do with this one, okay, because of that, is we can calculate it. It's still exclusive because it's going to be a king or a queen, but not both. All right? So what we're going to talk about here is drawing a king is 4 out of 52. And we'll add it to our drawing a queen, 4 out of 52. So our probability of doing that will be 8 out of 52, which would be the same as 2 out of 13. So this kind of question is what we did yesterday, okay, where you could do something or another. Okay? Now this one is pretty neat, drawing a king and a heart at the same time. So this one is also exclusive. I know, tricky. Okay? Because we have 4 kings, but only one of them is a king and a heart. How many of them are king and a heart? Only 1 king of hearts, so 1 out of 52. The problems that get tricky are not mutually exclusive, like this one. This one is our only not mutually exclusive. Now, why is that? Because it can be a king or a heart, okay? So we've talked about this thing. We have 4 kings in our deck of cards, okay? It's right here. That's where we got that information. 4 kings in a deck of cards. But we also, okay, have hearts in our deck of cards. And if we go back to our deck of cards, okay, we have 13 of those. So I have 13 hearts. I have an ace, a 2, a 3, a 4, a 5, a 6, a 7, 8, a 9, a 10, a jack, a queen, and a king. What's going to be important when we have our not exclusive events is one of these overlaps. What about the king of hearts? If we don't subtract him from our problem, okay, you've counted him once in our 4 kings and once in our hearts, and we don't want to count him twice, we only want to count him once. So we need to subtract the overlap, and that's the key here. Okay, we're going to subtract the overlap. Now luckily our denominator is all the same, so we will have 4 plus 13, which is 17, minus 1, which is 16 over 52, which does reduce to 4 over 13. Okay, so in our first not mutually exclusive event, we will have 4 over 13 chances to draw a king or a heart. Let's do 2 more examples, okay? Again, if I know their first thing we're going to do is decide, is it exclusive or not mutually exclusive? So there are 5 nickels and 5 dimes in your pocket. 4 of the nickels and 2 of the dimes are Canadian. That means the others must be American currency. The others are US currency. Okay, you randomly select a coin from your pocket. It is a dime or Canadian. Okay, right. So first thing we're going to do is we're going to decide, is that mutually exclusive or not? This one is not mutually exclusive, okay? This one is not mutually exclusive because it can be a dime and Canadian at the same time, no problema. The next thing I strongly suggest you do, and successful math students do, is draw it out. I have 5 nickels and 5 dimes. Okay, so I have a total of 10 coins in my pockets. 4 of the nickels and 2 of the dimes are Canadian, so I'm going to mark those with C's. Canadian nickel, Canadian nickel, Canadian nickel, Canadian nickel, Canadian dime, Canadian dime. So the other ones are my regular nickels and dimes. So now I can sort of visualize what's in my pocket. Next, I'm going to write my equation. So I know it will be something plus something minus something because it's not mutually exclusive, right? My denominator will be my sample space, the number of coins in my pocket, of which there are 10. So I'll have something over 10 plus something over 10 minus something over 10. Hopefully that makes sense. Okay, so my first one will be the number of dimes total. All right, so I'm going to circle all my dimes. How many dimes are there? 5. 5 dimes. Okay. Next is it is Canadian. All right. How many things are Canadian? Well, I've got these 4 and those 2. Okay. 4 plus 2 last time I checked is 6. We will now subtract the overlap. Okay, which is going to be Canadian dimes. And you'll notice when I said overlap, I meant that quite literally. If you drew it out how I showed you, okay, you literally have overlap. Right here, there's our overlap. Okay, that literal overlap is 2, so we don't want to double count our Canadian dimes. So we will have 5 plus 6, which is 11. 11 minus 2 is 9. 9 over 10. You have a 9 out of 10 chance of drawing out of your pocket a dime or a Canadian currency. And that's how you do these problems. Let's look at another. A box contains 4 red playing cards and numbered 1 to 4. The box also contains 4 black playing cards, numbered 1 to 4. You randomly pick a playing card. It is red or has a number less than 2. So, can we do something where it's both? Can it be red and a number less than 2? Yes, so we're at not mutually exclusive. Okay? So I'm going to draw it out. I have 4 red playing cards. 1, 2, 3, 4. So beautiful. And I have 4 black playing cards. 1, 2, 3, 4. And they're numbered. Red is 1, 2, 3, 4, and black is 1, 2, 3, 4. So now I know exactly what we're looking at. So I'm going to set up my equation. Okay. My equation is something plus something minus something equals my answer. The denominator is total things. I have drawn 4 because there are 4 red and 4 black, so there are 8 total in my sample space. Okay. So the first one is, it is red. How many cards are red? 4. This one's really tricky. Less than 2. 2 is not less than 2. So I have 2 cards less than 2. And then I have my literal overlap. Okay. So you see it. like I do. Okay. Overlap. I'm going to subtract the ones that are red and less than 2. So 4 plus 2 is 6. 6 minus 1 is 5. My probability of drawing a card that is red or less than 2 is 5 out of 8. All right, your problems are 12-fold. You have to do these 12 times. There are some of these that are not mutually exclusive, okay? So you got to look at them that you can do 2 things at once. I'm going to give you a hint, okay? Can something be an apple and a peach at the same time? No. Can something be red or blue at the same time? No. Can something show a 2 or a 5 at the same time? No. All right, so I've given you some hints there. Hopefully that helps. Do your best. Remember, it will always be fraction plus fraction minus fraction equals fraction. Okay? And keep in mind, it's very, very helpful to draw them out. For instance, number 1, we have 6 blue, 1, 2, 3, 4, 5, 6, this is number 1, and 4 green. Green. All right, so some of them fit well and some of them fit badly. So we're going to say the ones that fit well, okay, 3 of the blue shirts, okay, and 2 of the green shirts fit well. All right, so when you do this problem, okay, it asks you for blue or too big. So you'll be looking at blues and everything that doesn't fit. Okay, seriously, draw it out. Really helps. All right, good luck with your assignment. I believe in you.